Welcome back everyone. So we are discussing the numerical problems. We have discussed 2 problems. Now again we will discuss other few problems in this class again. Okay, so let me write down the problem first again. The problem is light from a discharge tube containing hydrogen atoms is incident, means light is coming, okay, on the surface of a piece of sodium the maximum kinetic energy of the photoelectrons, okay, emitted from the sodium is 0.73 electron volt. The work function of sodium is, the work function phi of sodium is 1.82 electron volt. Now they have asked to find the energy of photons responsible for the photoelectric emission okay. And the second question is the quantum number of the 2 orbits in hydrogen atoms, okay, the quantum number means the n value the hydrogen atom involved in emission of photons. And the third one is, this is a long question, the change in angular momentum of the electron of hydrogen atom in the 2 orbits. Okay, so there are 3 questions. So what is the picture? There is a discharge tube, okay, in that discharge tube, let me draw a discharge tube, there is hydrogen gas, okay. Now a light is coming from the discharge tube, how we don't know, that's not our business in this problem. A light is coming out and it's imposing in a sodium metal, and due to that collision of the photon with the sodium metal, what happens, the electrons are emitting, that means the photoelectric effect is happening, okay, and the kinetic energy of that electron is given, that is 0.73 electron volt. The work function of the sodium is also given, 1.82 electron volt. Now they have asked the 3 questions. The first question is, this is actually the hydrogen gas, okay, the energy of photons responsible for the photoelectric emission. What is the energy of the photon? Okay, this is the photons which are responsible, this is the photon which are responsible for the emission. So h nu is given, so we know from the our photoelectric effect chapter, that h nu is given electrons of the sodium metal, and first it is providing the work function to the electron, which is phi, and the rest of the energy is converted to the kinetic energy of that electron. So, that is the maximum kinetic energy. Okay. So, that maximum kinetic energy is also given, which is 0.73 electron volt. So, phi is also given, it is 1.82 electron volt plus 0.73 electron volt. So, it is eventually 2.55 electron volt. So, it should be the energy of the photon that is given, that is colliding with the sodium metal, and after collision electron is coming out. During that process, we know the amount of energy required for that kicking out of electron from the metal surface is called the work function, that is 1.82 electron volt, and after coming out from the metal surface, the rest of the energy of the photon is being utilized for the kinetic energy of that electron, which is 0.73 electron volts. So, straightforward. So, first question is done. Now, the next question, they ask the quantum number of 2 orbits in the hydrogen atom involved in emission of photons. Okay. So, this photon is emitted from the hydrogen atom, certainly there is some de-excitation, that is why the emission is occurring there. Okay, and the energy h nu is actually that E2 minus E1, we know. So, now we have to find out what is the formula for hydrogen atom. En equals to minus 13.6 by n square. Just we have to write it down here. So, it will be n2 square minus n1 square. So, this is the case. So, if you take common, then it will be h nu equals to 13.6 1 minus n1 square minus 1 minus n2 square. Okay. So, now h nu is given. H nu, what was the h nu? We have calculated 2.55 electron volt. Now, we have to find out. This is also in electron volt, there is no issue as such. So, now we have to find out the n1 and n2. Okay. We have to here just we have to use the trial and error, otherwise, because here is we have only one equation and we have two unknown quantities, n1 and the n2. So, eventually we have to do the trial and error. Let us put n1 is equal to 1, means where the electron is coming, ground state, n2 is the excited state. If n1 is equal to 1, then it will be 13.6 1 minus n2 square. So, it is 2.55. So, eventually 1 minus 1 n2 square is, let me calculate it, it is 2.55 divided by 13.6. So, it is actually 0.1857. So, 1 by n2 square is 1 minus 0.1875. So, it is 0.1825. So, n2 square will be 1 divided by 0.8125, it is 1.230 something. So, n2 will be just root over of that answer. So, it is root over 1.230, it is 1.10. So, we know this is not a precise value, 1.10. We know that n is actually the quantum number, it can take only the integer value. So, this is not true, this is the wrong, I am saying n is not equals to 1. So, next we have to consider the n is equal to 2. Okay. So, if n is equal to 2, then it will be 4. So, it will be 1 by 4. So, if it is 1 by 4, then 1 by n2 square will be 1 by 4 means 0.25 minus 0.1875 is 0.6. So, it will be now 0.0625. Okay. So, n2 square will be 0.0625, if you put, it will be 16. So, it is essentially be the 16. So, n2 is actually 4. So, it's clear that it's the correct, because it's coming exactly correct. So the transition is occurring from n equals to 4 to n equals to 2. That's our second question. What was our third question? It's also already answered. The change in angular momentum of electron to orbits. Okay, so change in angular momentum, del L will be L initial minus L final. So L initial is actually L4, L final is L2. So we know that L is equal to MPR equals to NH by 2 pi, we know that, right? MPR equals to NH by 2 pi, this is L. So it's actually 4H by 2 pi minus 2H by 2 pi. So 2H by 2 pi, so it's actually H by pi. Okay, and H by pi we have to calculate. H by pi is 6.626 10 to the power minus 34 joule second divided by pi is 3.14. So we can calculate this, there is no issue. So what will be the value? It's eventually 6.626 divided by 3.14. Okay, so it's 2.11 into 10 to the power minus 34 joule per second. So this is the change of angular momentum. Okay, so I think this question is also be easy question, is not that much difficult. Okay, so coming to the next question, question number 4. In absorbing (10.2) electron volt energy, the electron of a hydrogen atom jumps from any initial orbit to next higher energy orbit. Okay, as the electron returning to the former orbit a photon is emitted. They ask the what is the wavelength of the photon. So it's very straightforward question, nothing is there. So this energy is required, this energy is used, 10.2 electron volt energy is used for the excitation. This excitation is occurred from n to n plus 1, some n to n plus 1. This energy is 10.2 electron volt that is given, right? And after excitation it is de-excited and it's emitting a photon. So H nu should be equals to 10.2 electron volt. So H nu should be equals to 10.2 electron volt. So 1 by lambda is will be 10.2 divided by Hc electron volt. So 10.2 into 1.6 into 10 to the power minus 19, this is joule, and H is 6.626 into 10 to the power minus 34 joule second, and C is 3 into 10 to the power 8 meter per second. So joule will be cancelled out. Okay, so this is the case. So it is 10.2 into 1.6 divided by 3 into 6.626 and 10 to the power 8, it will be 34 will be there, so it will be 10 to the power 15 plus 15 10 to the power 7 meter inverse. So we have to just calculate this. So it's essentially be the 10.2 into 1.6 divided by 3 divided by 6.626. It's 0.8210 into 10 to the power 7 meter inverse, if I'm not wrong. Okay, yes, it's correct. Now we have to just change the sign. If we have to consider it's 10 to the power 7 meter inverse, we can convert it into 10 to the power, okay, 1 Armstrong is 10 to the power minus 10 meter, right? So it's 10 to the power 7. So just we have to do it. It will be 8210 Armstrong, if I'm not wrong. Okay, no. Okay, there is a mistake. This is meter inverse, right? What was the value? It's 0.8210 into 10 to the power 7 meter inverse. Now we have to consider the lambda. We have to take the inverse. So it is 1 divided by 0.8210. Yes, it's actually 1.2180 into 10 to the power minus 7 meter. Now we have to convert it in lambda. So it will be into 10 to the power minus 10 meter. So this is the wavelength. This is the wavelength of the emitted photon. Okay, so in this way you can calculate the lambda. So in this part, let me stop here. In the next part also we will discuss another 2 problems, and in next class also we will go through some other problems, and then the overall chapter will be completed. Okay, so let me stop here. We will meet again in the next part.